Hello students, I am VK Singh, the physics teacher, and today I will start discussion of geometrical optics, that is your photometry. I will begin with photometry. Photometry is the branch of physics that deals with measurement of luminous energy. Luminous energy is what? Light is an electromagnetic wave. In electromagnetic wave, two portions are there, one is visible and one is not visible. So photometry is measurement of luminous energy. Luminous energy. Now if we talk about light, this is your electromagnetic wave. In this electromagnetic wave, one is visible, whose range is 400 nanometer to 700 nanometer. 1 nanometer is equals to 10 to the power minus 9 meter. Now this tells about violet, and this is your red, and other portion is your invisible. Photometry is basically related with this region, visible region only. Now photometry is related with this visible region, in which 400 nanometer to 700 nanometer, that is the range, violet to red. In order to understand the photometry in a better way, few terms are there that needs to be explained. So I am discussing terms used in photometry. Terms used in photometry. So first term I will tell, that is your radiant flux. Radiant flux. Flux to flow. Flux is basically flow. So radiant flux is basically your total energy, visible and invisible, both region we have to consider. So total energy coming out of a source. So this is your radiant flux coming out of a source per second. So what should be its unit? Its unit is watt. I will represent it by the symbol R. Now after this radiant flux, I would like to introduce a new term, that is your luminous flux. Luminous flux. Symbol I will give as phi. Luminous flux. Luminous flux is luminous energy emitted per second. This is total energy, and this is luminous energy emitted per second, that is from 400 nanometer to 700 nanometer. So luminous flux has got a specific unit, that is your lumen. Lumen. Symbol is your Lm. So dimensionally luminous flux and radiant flux are same, but in unit wise they are different. Naturally there should exist some relationship between this watt and lumen. So 685 lumen is equals to 1 watt. This is the of a specific wavelength 5550 angstrom. This 5550 angstrom, that is 555 nanometer. This value has to be remembered because human eye is most sensitive to this wavelength, and this is in your green yellow region. This is in your green yellow region, 555 nanometer. And what is angstrom? 1 angstrom is your 10 to the power minus 10 meter. So luminous flux is this, radiant flux. Now after that, the next term that I will introduce is your luminous intensity. Luminous intensity, or it is also known as illuminating power. Illuminating power. I will represent the symbol I for it. Now you see, luminous flux is the characteristic of source of light. Luminous intensity or illuminating power is also the characteristic of source of light. How can we define it? It is defined as, I is defined as luminous flux per unit solid angle. Luminous flux per unit solid angle. What is solid angle? The angle that the cone 3-dimensional angle. So the complete value of solid angle is your 4 pi. 4 pi for a sphere. For a sphere, if the at the center of a sphere, the complete angle made by the sphere at the center of a sphere, solid angle is your 4 pi. So we can write phi by 4 pi. Unit is what? Steradian. Unit is steradian. So a very important formula we are getting here, and what is that? That formula we are getting, phi is equals to 4 pi I. Phi is equals to 4 pi I. This formula has to be understood. Phi is equals to 4 pi I. This is the relation between luminous flux and luminous intensity. Now, luminous intensity is unit. What will be the unit? Unit will be lumen per steradian, and lumen per steradian is called candela. Lumen per steradian is called candela. So lumen per steradian is the candela that you have read in your base units. 7 base units are there. Out of 7 base units, 1 is the candela, lumen per steradian. Here, next term that is required in your photometry is your illuminance. Or intensity of illumination. I will represent it by the symbol E. Illuminance or intensity of illumination, I will represent it by symbol E, and its definition is, basically you should understand that this is the characteristic of source, not the source but the surface. It is the characteristic of the surface. This was the characteristic of source, this was the characteristic of source, and this is the characteristic of surface. It is defined as E is equals to luminous flux per unit area, phi by area. So unit wise, it has got the name lumen per meter square, and this is called your lux, and lumen per centimeter square is called your fort. You can get the relation between them. So this tells about your illuminance or intensity of illumination. Next thing is there that is to be understood in discussion of photometry is your efficiency. Luminous efficiency. Let us talk about luminous efficiency. Luminous efficiency has the symbol eta. This is the ratio of luminous flux to radiant flux, and basically it is a dimensionless quantity and it has got a unit, lumen per watt. It has got a unit, lumen per watt. So this is the unit for, initially the incandescent bulb was there, its luminous efficiency was very less, so it was improved, and now then came the fluorescent tube light whose efficiency was more, then came the CFL whose efficiency was even more than the fluorescent lamp, and then it came LED. So basically, to increase the luminous efficiency in the illumination engineering, this type of technological changes takes place. So lumen per watt, this is your luminous efficiency. Next thing is there that we would like to discuss, inverse square law. Here E is equals to phi by area. If we consider a spherical body, phi is your 4 pi I by E, area is your 4 pi r square. So 4 pi will cancel, E is equals to I by r square. This implies E is proportional to 1 by r square. This quantity, this relation is known as inverse square law of photometry. Inverse square law of photometry, valid only for point source of light. Valid only for point source of light. It is not valid for your tube light. For bulb like situation it is valid. So this is your inverse square law. Then it comes Lambert cosine law. So as the distance increases, the illumination of the surface goes on decreasing. Lambert's cosine law. If a surface is xy and it is falling in this way, the luminous flux on this surface, then E is equals to luminous flux by area of xy surface. Now if the surface is tilted by an angle theta, then dash y is equals to sec theta. So E is equals to phi by area of x dash y, and area of x dash y has increased and it becomes, so E is equals to x dash y, that is your phi by a sec theta. So E is equals to phi by E dash, better you say E dash, phi by A cos theta. So E dash proportional to cos theta. What does it means? That if we tilt the area, illuminance goes on. Here the illuminance is maximum, and when this area will become in this way, the illuminance will be minimum. It will be 0. So here the area, here the angle is 0, so the illuminance is maximum, and here the angle, as it increases, illuminance goes on decreasing. So in general, E is proportional to cos theta is called Lambert's cosine law. E proportional to cos theta is called Lambert's cosine law. Now this has got a very good example in our day-to-day life. What is that example? The sun, the distance of the earth from the sun remains the same in the morning time also, in the midday noon time also. But midday noon time we feel more heat, and the reason is that in this way the angle is nearly 90, so heat is less, we feel less hot in the morning, and in this time when the sun is after the head, we feel more hot. Why? Because at this time the angle is 0, nearly 0. So this is your Lambert cosine law. After that, now we have to understand the photometer. Photometer is a device which is used to compare the luminous intensity of two sources of light. So this photometer is a very simple, it is an experimental arrangement in which a screen is there on an optical bench. Here is one source S1, here is another source S2, this distance is R1, this distance is R2. Here generally a grease spot is taken, Bunsen grease spot. This represents your grease spot. This is your cardboard like situation, cardboard. So what we observe? We observe that by suitably adjusting the distance R1 and R2, we are in a position to get equal illumination of the grease spot, and in this situation E1 becomes equal to E2, and then I1 by R1 square, I2 by R2 square. So I1 by I2 is equals to R1 square by R2 square. This is called comparison. So what can we understand? We can understand that just by measuring the distance R1 and R2, we can easily find the ratio I1 by I2. On the optical bench we can measure the R1, R2, and we can find the relation comparison I1 by I2. And this much is sufficient enough for you people to do the questions of photometry. Photometry questions can be easily solved by these few concepts. Now see the example. A lamp produces certain illumination on a screen placed at a distance of 120 cm from it. On placing a transparent sheet of glass between lamp and screen, 25% of light is stopped. Find the distance which the lamp should be moved towards the screen so that the illumination remains the same. In this situation, here you see first case, E1 is equals to I1 by 120 square. First situation, 120 centimeter is the distance from lamp. When the lamp is covered with glass, then it reduces the intensity, and that intensity is 25% stops. 25% light is stopped, so 75% is available. So for second situation, the intensity is 0.7 I1. So E2 will be 0.7 I1 if the distance moved by the lamp is x, then 120 minus x whole square will be there. According to question, this E1 is equals to E2. So E1 is equals to E2, and by solving this you will get x is equals to 16.08 centimeter. What does it mean? It means that if you will move the lamp 16.08 centimeter towards the screen, that is towards the glass sheet, then the illumination of the screen will remain same. So this was the matter that you should understand very carefully, that here the lamp is there and lamp is covered by glass. So two situations is there. One situation when the lamp is not covered by glass sheet, and in another situation the lamp is covered by glass sheet, and in both the situation you want the same illumination. So same illumination, for that what we have to do? We have to move the lamp nearer towards the screen, and that distance we have calculated as x centimeter. Here you see, luminous efficiency of a lamp is 5 lumen per watt if its luminous intensity is 35 candela. Find the power of the lamp. So eta is equals to how much? 5 lumen per watt. I is equals to how much? 35 candela. Luminous efficiency is what I have said, phi by electrical power P. So P is equals to how much? P is equals to phi by eta, but here it is I given, so phi is equals to 4 pi I. So P is equals to 4 pi into 35 by 5. That means power of the lamp is 88 watt. A student has a very good confusion in luminance and illuminance. This thing has to be clearly understood. Illuminance and luminance are not same. Whenever you are using a bulb, the light falls on the surface and then a portion of it reflects towards the observer and goes to the eye. So what is falling on the surface, that is illuminance. What is falling, incoming light, that is illuminance, that illuminates the surface. And the luminance is the perception, human perception of brightness. So brightness and luminance are also not same. Why? Brightness is a subjective quantity which cannot be measured, whereas luminance is an objective quantity which can be measured in unit candela per meter square. So measuring what is leaving the surface and it reaching the eye, that gives you luminance, and what is falling on the surface, that tells about the luminance. One thing you also understand, lux has a very great importance in our day-to-day life also, because in the lightning arrangement we have different types of lux level required. For example, in day-to-day reading process we need around 300 lux for reading purpose. For looking, understanding, or in a corridor we need 80 lux, that makes the things visible. In a full moon light you will be getting 1 lux, in a street lamp you will be getting approximately 10 lux, whereas in case of operation theater you will be needing 10,000 lux. So these are the things the illumination engineer tells about this thing in a more detail, that lux level is determined according to the requirement, because reading requirement is different, operation requirement is different, and similarly sleeping lamp has a different lux level. So in this way we have to understand the lux level also, and we have to understand these matters in a very careful way. Hope this discussion of photometry will help you in preparing the exam in a better way. In the next discussion I will continue the matters related with the geometrical optics.